To understand Newton's laws of motion, we first need to develop the idea of a force. A force will ultimately be the cause of a change in motion. Now, a force is most simply understood as a push or a pull on an object. And this push or pull is a vector, because you can push with a certain amount of force or strength. That's the magnitude, and you can push or pull in a certain direction. So forces are vectors, and there are many types of forces in nature, and there are a few different ways of categorizing them. So one way to categorize them is to distinguish between contact forces and field forces. Contact forces are what they sound like. It's when two objects are in direct contact, they're touching. So a contact force is what's between my hand and this notebook, so that I can pick up the notebook and move it around. So contact forces are when objects are directly touching. So examples could be holding a book, it could be kicking a ball, there's contact force between your feet and the ground when you're standing. There's a contact force between wheels and the road when you're driving. I think you get the idea. Anytime two objects are touching, they are applying a contact force between them. Now, the other category of force is maybe a little bit harder to picture. This is a field force. Field forces do not require direct contact to produce the push or pull, but these still happen all the time, and you are familiar with them. Gravity is a field force. So if I take this pen and I drop it, there is a force of gravity on that pen. That pen is getting pulled by the earth toward the ground, but the pen is not in contact with the earth, at least when it starts to fall. Those two objects, the pen and earth, are not in direct contact, yet there's still a force between them. That's a field force. In fact, any two objects exert a gravitational force between them. All two objects in the universe are pulling on each other via this gravity field force. Now, another field force that you've probably experienced before is the magnetic force. If you've ever played with magnets, you have noticed that you can feel them attract or repel even when they're not touching. That works at a distance without the magnets being in contact with one another. So magnets generate a field force. Now, there's some other field forces. They're maybe less common in your daily experience. There's the electric force. You might have noticed an electric field force if you've ever tried to like take a balloon and rub it on your head and stick it on a wall, or maybe you've taken laundry out of the dryer and you've noticed a prickly electric sensation because those clothes are electrically charged and you can feel that electric force. In Physics 7, we spend a lot of time discussing the electric and magnetic forces. So all these forces act at a distance. They are field forces. Now, what's really interesting and kind of mind-blowing if you think about it a lot, all of these contact forces are really just a manifestation of the electric force. So let me explain what I mean. The fact that objects feel solid is because the electrons in one object are repelling the electrons in the other object via the electric force. Like charges repel. So the fact that materials feel solid is really, when you look at it in a microscopic sense, it's electrons repelling electrons, and they're doing so via this electric force, and in some sense the objects never touch. In another sense, that's what touching is. Objects touching is when they get close enough that the electric repulsion between electrons in adjacent objects becomes noticeable. So really, on a microscopic level, all contact forces are just the electric force. But as far as we're concerned in Physics 6, we can say contact forces really exist. We'll just talk about objects touching. That's fine. We don't need to think about what's happening at a subatomic level. But if you want to keep that picture in the back of your mind, think of the structure of an atom with orbiting electrons around a nucleus, and when objects are touching, adjacent atoms have their electrons repelling one another via this field force. Now there's one other way to categorize forces in nature. That's to list the fundamental forces. So as far as modern physics theories are concerned, you can describe all forces in nature as falling into one of these fundamental categories. And this overlaps a little bit with what we said over here. These four fundamental forces are the strong nuclear force, that holds nuclei together. Then there's the electromagnetic force, where really magnetism and electricity are different aspects of the same fundamental phenomenon. There's the weak nuclear force, that governs nuclear decays. And there's gravity. So I listed these in decreasing order of strength. The strong nuclear force is the strongest force, but it's also very short range, so it only is important inside nuclei. The electromagnetic force is long range, and as I said, we see this all the time. This is the kind of the dominant force in our everyday lives. The weak nuclear force also only works at a very short range inside of nuclei. And then gravity is by far the weakest of all these forces. But we still do notice it in everyday life because gravity depends on mass. And so if you happen to be near something that has an enormous mass, then gravity becomes significant. And we happen to be near something with enormous mass, that's planet Earth. So we do notice the effects of gravity in daily life. But if you were to calculate the gravitational force between two electrons compared to the electric force between two electrons, it would be totally insignificant.